Experiment number 5, verification of the law of parallelogram of forces and using it to determine the mass of a body. Right. So let's see what are the materials and apparatus required for this. So there is a different apparatus, parallelogram of forces apparatus. The board, right? Wooden board usually. So on the board you have 2 pulleys connected, which are almost frictionless. We can't say it's 100% frictionless, but almost frictionless. And on the board we can paste, or we can fix a piece of paper to trace. And the other apparatus we require in this is that we need a set of masses, unknown masses, a set square, a plane sheet, a mirror strip, a half-meter ruler, and the beam balance, the triple beam balance. Right, so let's see how do we do this experiment. Right, so there are scale pans here in this device, and there is a string. You can see that we have this string and this string. So we can say it's either 2 strings or 3 strings, right? Okay, so let's see how do we verify that the law of parallelogram vectors is correct using this. Okay, you know what the law of parallelogram vectors is. If you have 2 vectors, or if you have 2 forces, you can find the resultant of those 2 forces by keeping those 2 forces as the 2 adjacent sides, of a parallelogram. And once you make the parallelogram, the common diagonal is going to give you the resultant. So this is the concept of law of parallelogram vectors. And to find the values, you know, there's an equation, r equals to square root of p squared plus q squared plus 2pq cos theta. So I'm pretty sure that you are very familiar with this. Right. So since you are familiar with this, no need to explain about the law of parallelogram vectors. We can go to the experiment. Right. So what do we do in order to verify this is that we take 3 known masses. Right. We take 3 known masses. So the weights of those 3 known masses, we can say W1, W2, and W3. Right. So we keep those 3 masses, as we can see here on the scale pans. And before keeping them on the scale pan, there is an important check that we need to do. Let's see what that check is. So we need to make sure that these pulleys are frictionless. So in physics, when we say frictionless pulleys, strings are going to slide along those pulleys. That is what happens in physics. But practically in real world, we cannot find pulleys on the surfaces which are frictionless. So the surfaces of those pulleys aren't frictionless. So what we do is we take pulleys with the bearings with the least friction. Now these pulleys have bearings, these bearings have least friction, so we can rotate the pulleys easily. So these pulleys aren't the pulleys that we find in questions. These pulleys are the pulleys which rotate, but they have the least friction, so we can assume that they are almost frictionless. But first, prior to doing the experiment, we need to check whether they have a significant friction or not. So how do we do that? There are 2 ways of doing it. First thing is that before attaching these strings on the board, on the apparatus, you can just punch, or you can just hit, you can just push the pulley a little bit, and you can make it rotate, and you can observe it whether it comes to stop quickly, or is it going to rotate like for some long time period. If you can see that if it comes to stop say like in a few seconds time, if it stops quickly, if you can see that there's a deceleration, quick deceleration, a high deceleration, if you can see that, then we say that has a friction. But if it does not stop, if it turns for like long time, then we can assume that they are almost frictionless. So in case if they have friction, what we can do is we can put some oil. So these are critical points you have to memorize. We can put some oil on the bearings, on the pulleys, so we can make them almost frictionless. Or else, if it doesn't work, if it's corroded, and say that it's corroded, the pulleys are corroded, oxided or whatever, if so, we'll have to replace the pulleys. So there are only two options in case that they have friction. One thing is that you can put some oil and try to make them frictionless again, or else you'll have to replace it. Right. So these are the this is the basic check that we have to do. Right. So once you do that check, then you attach the strings, and then you put the three weights like this, as shown in the diagram. So we can also check, there's another way to check whether there is friction, significant friction is there, by using these weights as well. So once you keep these weights, they will get themselves adjusted and they'll come to an equilibrium position. So think that this is the equilibrium position. So when it comes to the equilibrium position, what you can do is you can just hold it, right? You can just hold the string, and you can pull it down a little bit. You hold the string and you pull it a little bit down. So when you pull it down and when you release it, you just pull it a little bit down. Any of these masses, you pull it a little bit down and you release it. So once you release it, if it comes back to the same initial equilibrium position, then we can say it is almost frictionless. But if it stops at different places other than the equilibrium position which was before, then it means it has friction. It has a significant amount of friction. There can be only one equilibrium position. So if the equilibrium position changes, if you pull it down or push it down a little bit, if so, there is friction. So it's not a good device to do the experiment on, right? Okay. So let's see how do we do the verification now. Right. So first thing is that since you know these masses, you can introduce a scale. You can introduce a scale, a mass scale, mass and length scale. So I will write a dummy scale here. So my scale here is that 1 centimeter represents 1 Newton. 1 centimeter represents 1 Newton. That is my scale. So since I know the weight of W1, W2 and W3, I know how much of centimeters that those vectors are going to be. What is the length of the vectors, right? So we have introduced a scale. Now what we are going to do is we are going to trace. Now on this board we have a white sheet. Usually we use an A4 paper on this board. Here you have a white sheet. Behind the strings we have a white sheet, and our purpose here is to trace these three strings on the white sheet. So let's see, how do we trace the string on the white sheet? Let's see, how do we trace the strings on the white sheet? So what we do here is that we use the set square, and there are two ways of doing this. Either we can use the set square, then we can trace it, or else the other way of doing it is that we can use the mirror. So there are two methods. One is the mirror method, one is the set square method. So I'm going to explain which is which. So the the set square method. So this is a string. This is a string. So what you do is you take the set square, you keep it on the sheet, you keep it on the white sheet. Now this is your set square, and you're going to keep the set squares this side of the set square, in a way that it is slightly in contact with the string. Now the set square is slightly in contact with the string. Slightly. It is not going to push the string. Slightly in contact. So from that you can trace the point just below the string on the sheet. Now you're going to mark the point just below the string on the sheet. And then what you're going to do is that you are going to take the set square and keep it at another place, and also at that place you do the same thing, and you are going to trace that point as well. So now we have traced the points, so you can remove the set square. As you can see in this, now I have removed the set square. So I have two markings on the white sheet. Now what I have to do is I have to take the white sheet out, and I can extend these two lines, these 2 points. I can extend the line joining these 2 points. This line is exactly directly below the string. So this is how we use the set square to trace the string on the white sheet, right? You may wonder, why do we need to do this? Because the white sheet and the string has a gap between them. There's a gap, so you can't do any changes to the string. You can't hold, you can touch it, you can't push it onto the sheet. No, you can't do that. If you do that, the experiment will change. So we are not going to disturb the string, and we are going to trace the string on the white sheet. So this is one method of doing it. So use a set square, you keep it at two or more different places, and then you trace the positions so that you can trace the strings, right? So this is the set square method, and the next method is the mirror method. So for the mirror method, we need a small piece of mirror. What you do is, now say that this is your string. This is the string, and we are going to place the mirror on the paper, on the white sheet. We are going to place the mirror on the white sheet. So on the white sheet behind the string. So you have the mirror between the white sheet and the string. So now you look from the top, look from above at the mirror. You look at the mirror from above. What you see is, you see the string as well as the image of the string. You can see the string as well as the image of the string. So assume that this is the image of the string that you see. You see the image of the string. So if you can see both the image and the string, it means that you are not straight above. You're not straight above the string. You're not straight above. So what you do is you move your head this way and that way, like that, until the image is covered by the object. Object is the string. You move your head here and there until the image of the string is covered by the string. So when you cannot see, now you can take a small piece of mirror and do this at home, right? So when you cannot see the image, at that point you're going to put a pencil below and you're going to mark this point. Means that you are going to trace this point using a pencil, and also you are going to trace this point. So now what you see is, you don't see the image, right? You don't see the image, you only see the string. So you're going to put a small dot here and a small dot here on the paper, and then you remove the mirror. So once you remove the mirror, you have two dots. You have two dots like this. Then you attach the two dots. So once you attach the two dots, that is the exact trace of the string. So likewise, you do it for all the three strings. This one, and this one, right? And you trace them. So you take the A4 sheet out or the white sheet out only after you trace all the three strings, not just one. You have to trace all the three strings at the same time, at once, at the same time, right? You can't take it out and put it back and again trace another one. No, you have to trace everyone at once, and then only you can take it out. Otherwise, if you take it before, it will change, right? So once you do that, you take it out. So when you take it out, what you can see on that sheet is two lines like this, another vertical line, so it's like looks like a Y. So we have traced. Now we are going to use the scale. 1 centimeter represents 1 Newton. So if W1, let's just put some assumed values. If W1 is 8 Newtons, and if W2 is 6 Newtons, you're going to mark for 8 Newtons, you need to mark 8 centimeters according to the scale. So you are going to mark 8 centimeters here. And for this W2, you are going to mark 6 centimeters here. 6 centimeters. So likewise, you are going to mark 8 and 6 centimeters based on the scale you have used. 8 and 6. Now what you can do is you can draw the parallelogram. So you draw a line parallel to this line here. You draw a line here that has to be parallel. So let's make sure that it's parallel. You draw it here, and you draw another line from here, which is also parallel to the previous. Let's check whether it's parallel. So this is a small check that I'm going to do. So in order to do this, draw this also, you can use a set square, and you know how to use a set square for this. And then you are going to draw the diagonal, which is going to show us the resultant of these two, the diagonal. So this was the before 8 Newtons vector, this is the 6 Newtons vector, and there was equilibrium under 3 of these vectors, right? So now we have the resultant. Here. So this resultant must be equal and opposite to this in order to achieve equilibrium. Now this was an equilibrium system. Now as soon as you draw this, you can see that this is wrong. You should be able to see that this is wrong. Why is this wrong? Now these three forces were in equilibrium before. So if now you need to go to mechanics to find out equilibrium under 3 non-parallel forces. They have to be concurrent, as well as the resultant of any two forces must be equal and opposite to the other one. So the resultant of these two forces is this one, but it is not just opposite to this one, because this is vertical and this one, the one that we got, is not vertical. So we have made some error while doing the experiment, or either there is friction in the pulleys, right? So what we need to do is we need to draw it. We need to do the practical perfectly. So if you have done the practical perfectly, this diagonal must be a vertical line, because this is always vertical, right? This is vertical, nothing else. So this has to be vertical, as well as when you measure. Now what you do next is that you measure this length. You are going to measure this length. So when you measure this length, let's say I'll take an example value. Once I measure this length, I'm getting 12 centimeters. When I measure this length, I'm getting 12 centimeters. So 12 centimeters should represent 12 newtons. So now you can check whether W3 is equal to 12 newtons or not. So this is how we do the verification. You take 2 and you complete the parallelogram. You draw the diagonal and you measure the diagonal, and you go back in the scale, you use the scale to figure out what is that force is equal to, as well as that has to be directly opposite to W3. So we say the law of parallelogram of vectors is correct if the value denoted by the diagonal is equal to W3, as well as the diagonal is vertical. Then we say law of parallelogram of vectors is correct. So it's proved. So this is how we verify the law of parallelogram of vectors using this device. And what if not? What if it is not equal to W3, and what if it is not directly opposite to W3? Then we have made a mistake. We can't say we can't say that law of parallelogram of forces is wrong. We don't say that because it's already proved. If it was like that, then we say yes, it's true. But if you don't get the expected results, we don't say it's wrong. Then we have to check our device. Well, then we have to redo the experiment until we get a proper result. So this is how we do the verification, right? So now let's see, once you do the verification, how you are going to find an unknown mass. So that's also very easy. So here, let's assume, we'll take the same example, and let's assume that we do not know W3, but we know W1 and W2. So let's assume that we know W1 8 newtons and W2 6 newtons, but we do not know the W3. It's the unknown mass. So you put these on the scale, then you balance them. Once you balance them, then what you do is that you're going to trace the strings on the white sheet once again. You trace them, then what you do is that you're going to complete the parallelogram according to the scale. 8 newtons is 8 centimeters. That depends on the scale that you take. You can't take a different scale if you want. And then you draw the diagonal, right? So the diagonal must be vertical. If it is not vertical, then also it's going to prove us that you have done some mistake. We have done a mistake. So that has to be vertical, this diagonal. Now in my diagram it's not vertical, but it has to be vertical when you do the experiment. So then you are going to measure the length of the diagonal, and then you are going to calculate using the scale what is the value of W3. So here we get that W3 is equal to 12 newtons. So that is how you find the weight of an unknown mass using this law of parallelogram of vectors. Right. So you must also think that there are scale pans here. So don't we have to get the mass of the scale pans as well? Because we assume that the tension here is equal to W3. We assume that the tension here is equal to W2. We assume that the tension here is equal to W1. So what is this W1, W3 and W2 exactly? So they are the total weights of these systems. So when we say they are the total weights of the systems, that means it's including the mass of the scale pan and the other mass, both of them. Yes. So we have to initially measure the masses of these scale pans. You can use the triple beam balance to do that. You measure each and every scale pan, then you add that mass also to the masses that we keep on these scale pans. So that is the sum is what we get as W1, W2 and W3. So it's a total mass. What we get as W1 and W2 and W3 are the total mass including the masses of scale pans. So that is a critical point that you have to memorize. Right. So this is how we do the practical. So remember the critical points I said. Those are the most frequently asked questions.